Cool, let's start. So my talk's on just add an index. So that's some boring stuff about me. I work at a company called Excellence, which is in Glasgow. We're actually hiring if anybody's fancying a new job. But before we get started, if people could go to that address on their phone, that'd be really useful. So we're going to have a bit of a quiz throughout my talk. To make it a bit more interactive. So if I flip to this, if my mouse gets and click play. Yeah, it should do. Is everybody on it? Has everybody done the first question? Yeah, people are doing the first question. Excellent. Cool. Anybody else waiting? No? So, this clicker thing's not working for some reason. So, I'm just going to go over the top performance problems with .NET applications, and this is probably applicable across like Java applications and any other applications. So there are four main topics if you search anywhere on the internet. Comes up with exception and logging too much. So we're throwing too many exceptions and logging them. Or we've got tons and tons of like debug logging, what we're dumping to like some database or some file system or maybe CloudWatch. Overuse of thread synchronization and locking. So we're kind of, instead of doing like patterns like swapping out memory addresses when you add a collection to make it faster, we're adding lots of locking around things, what blocks loads of threads, makes things a lot slower. Network connectivity, so from your application talking to your database or to some kind of other cloud service or APIs. And also then slow database calls. So there's not usually much about kind of slow .NET applications when it comes to like actually writing the code. They're all just like external factors. And the one we're going to look at today is slow database calls. So the first thing when you get a slow database call, your kind of senior dev comes to you and goes, just add an index. So that's where this talk comes into play. So everybody just add an index. So the first question we're going to do is, what index should we add to this table? So we've got 5 items in this table with first name, last name, age, city, favorite color. And we're doing a select star from person where age is 30. So we're querying this is a person table, and we're trying to get the exact records where the age is 30 in this table. So we've got an index which is age ascending. We've got another index which is age descending. We've got an ID ascending index, and we've got don't bother adding one to any at all. So I'll just flip back to my little quiz, and people can vote on it. So feel free to vote which one answer you want. So most people are putting age ascending. Cool. I'll tell that most people voted. So for this table, we probably better just add no index at all, because you could probably fit that table in RAM on a Raspberry Pi of like 1 gig. And it wouldn't even use it, the index, if you actually put it on there, because it has to go traverse the index and then go look it up from the clustered index. So the actual answer is none. So actual answer is none. Oh, somebody actually did vote that one. It's just reordered them for me. That's nice of it.
Will that remain true if you have millions of records?
Oh, calm down. So,
Next slide.
So this is a similar table. This time we've got 9,542 records in it. And it's exactly the same. We've got first name, last name, age, city, and favorite color. This time we've got a bit of a different query. We're trying to search for the age is 75, but we're also getting all the records from it. So we've got the same indexes, age ascending, ID, and none. So I'm just going to flip back to this. And if people want to just vote for that one. should probably do the next thing first. So I think most people have voted. So people put age ascending and age descending. So these are the common ones that you normally add, but sometimes it might not use them as well. So you might be better, if you've got a load of RAM on your machine, which is really fast, you might be able to just put that whole table into RAM, and you might be able to just traverse that whole table. But if you've got other things happening on that machine, maybe you've got lots of other different tables, lots of other different indexes, it might be beneficial to add an index of age ascending and descending, or descending actually. So it doesn't really matter which one you actually use of that. But it's easy to fall into a trap of adding an index to every single column. So when your senior developer comes to you and says, just add an index, now you know which index to add because you've got lots of rows in your table and it's been slow. So this time we get first name. We add an index on first name because we're querying by the first name. Same thing for last name. Same thing for age. Same thing for city, and then favorite color. And now we've got more indexes than table columns, which is not where you want to be. So adding an index onto every column is bad practice, and you just end up consuming more memory of indexes than actually what the table would be to just put into RAM itself, and then just kind of scan through it. So we should always strive to cover the most amount of queries with the least amount of indexes. So this is what people should keep into mind when they're thinking about kind of adding more indexes. So we're going to cover a few more questions. So we've got can we utilize this index now? So if we've got a compound index on age ascending and first name ascending, and we've got a query of select star from person where age is 40, can we use that index above to do that query? So I'm just going to flip back to my little poll and find my cursor. So feel free to vote yes or no. I don't know which one's yes and which one's no. Get a tie. Ooh. Cool. So most people said yes, which is good because we can use that index. And the reason why we can use that index is because it's the first on the left-hand side, and we can do a direct seek down the actual the index to get it. And we'll talk about seeks and scans later down the line. So this is an index seek because it's on the far left-hand side. The same table, and this time we've got the same index of first name and age, but this time we've changed our query around a bit. Actually, the first name and age, but we've swapped them around so they're different. But we've got the same query of saying whether age is 40. So can we utilize the index of first name and age when we've got that query of whether age is 40? So I'm just going to people vote. Okay, it goes 50-50 straight away. It's good. So which one's winning? So no is actually winning, but the answer is actually yes. So technically this is not as efficient as the last query, what we actually wrote, but you can use that index to actually go find that column. And the reason why is it's still part of the actual leaf node of the index, so it's still the end. So we can do a scan across the whole index to find all the ages, and that's called an index scan. So that's a big difference between index seek and scan, and we'll kind of show that in a second. So indexes are all based on B trees, which is a balanced tree, and trees in computer science are always upside down, so they look like that. But they kind of look like this. So we have a root node, some intermediate layer nodes, and some leaf nodes. And you kind of traverse down it pretty much like a binary tree. So you go down the tree to find your records. And this is our age ascending index, but as a tree form. And what we've got here, I can use this pointer, can't I? So what we've got here is our root node, which says everything between 1 and 50 is on the left-hand side, and everything above 50 is on the right-hand side. So if we've got a value here, which is 3, we can pop into the left-hand side, and then we can then do exactly the same thing. Where's 3 between 1 and 30? And it's on the left-hand side again, and it'll be here if it was existed. But there's no 3 in this, for example. So for our query where age is 40, for example, That'll go to the left-hand side down that branch, and then it'll also go down the right-hand side to that branch. You'll find where 40 is, and then it'll have a reference back to the clustered index, which on this one is 7, and then it'll go find the record in the clustered index instead. So that's kind of an index, that is an index seek. So you're seeking down the tree. We can also do queries where the greater than, for example, so we don't have to do exact values. We can utilize the index for that as well. So it's the same index, but a different query. And this time we just go down the tree like this. 40 is greater than 30, back to 40 on the right-hand side. We'll go get 7, and it'll just scan the rest of the index. So all these nodes at the bottom of the index here, you can keep jumping through the leaf nodes. And that's kind of how it finds the rest of the records where the age is greater than 40. A bit more complicated. So now we've got age ascending and first name ascending index. And we've got a bit of a different query up here. We've got where the age is 30 and the first name is D. And it works exactly the same because you just basically go into the left-hand side if it's lower and right-hand side if it's higher. So we're looking for 30 in D. So 30 in D is going to be on the left-hand side. It's going to be on the right-hand side of the 30 in A because D is bigger than A. And then it's going to look in the leaf node and find 30D. And then it's just going to go find that record, and then it's going to fetch the actual the row for that record. So it works exactly the same, totally exactly the same. This one's a bit differently. So we've got it's the same query, but a different index. But because we've got the age ascending and the first name ascending, like we did in the question at the start, that means we can use the left-hand side of it to just traverse the tree. So for this example, we can say where the age is 30, it's got to be on the left-hand side, and then it's got to be on the right-hand side of that. But then there's multiple records where you've got a first name of A, D, and X. So it just goes to all them records and gets all the values for them records, what it needs to get. So that's why you can still utilize that index in that first pop quiz what I did. So this is the other, the index bit reversed. Well, the query is reversed. So now we're looking at the first name querying on the first name, but not the age. And as you can see, we can't traverse this tree because we don't have the left-hand side part of it. So what we can do is just scan the leaf nodes at the bottom here. So what it does is just scans the bottom of the leaf nodes of the index, finds the ones where it's A, so that one's A, it's got that one, goes to the next one, that one's A as well, it's got that one, that one's A on that leaf node, it's got that one, and then there's no A's on that node as well, and that's the index scan, so it's just scanning the leaf nodes of the index. So that's why it can utilize it in both different forms, but this is not as efficient as doing an index seek. This one's age ascending and first name ascending index. So that, I don't know why. So that goes down the left-hand side to 1, and because there's multiple of 1, we can just go to them records and get them. Oh no, wait a minute. This query. Sorry, I'm going a bit ahead of myself. So this one is specifically getting the first name. It's not doing a select star, so it doesn't have to go and get the record from disk. But it's got where the age is 1, and because this leaf node contains the first names, so it's got A and B, it doesn't actually have to go to fetch the actual record from the clustered index. So that's pretty much the end of my talk. So some takeaways really is try to use the least amount of index to cover the most amount of queries. You want high cardinality indexes, so they would need to be very selective. You're better at having selective indexes than less selective indexes, so then it has less to scan. Always drop indexes that are not used, and you should monitor that. And always keep an eye on performance, because performance changes over time. So as you see in the first one, we had 5 items in a table, and that probably didn't need any index to start off with, but once it grew, it probably did. And to be fair, this is only touching the surface of performance in databases, but it's just generally some things what people say to people when they're actually looking at query performance. They're just like, just go and add an index, and then people just add an index on every column and make it slower. So yeah, I hope you enjoyed it. Thanks.